Welcome students to MOOC's series of lectures on non-parametric statistical inference. This is lecture number 2. In the last class, we have seen how to do point estimate for different quantiles. Today, we shall start with estimation of central location. When we talk about parametric inference, by central location typically we think about mean, but in a non-parametric scenario, the major central location that we consider is median. In the last class, we have seen how to do zeta p for 0 less than p less than 1, and we have found out the point estimate and interval estimate for zeta p for any given p. When we are looking at median, then value of p is 0.5. Therefore, effectively we can estimate median in a very similar way, the way we have done for any arbitrary p, by considering the value of p is equal to 0.5. So, consider for example, this set of data. There are 11 data points 29.7, 26.1 up to say 11.4 and 45. From here, what we do, just to recollect that, we take the ordered sample, that is we sort them in increasing order. Since value of n is equal to 11, therefore, n plus 1 is equal to 12, and hence n plus 1 into p, which is 0.5, that will give us 6. Hence, the point estimation for median is x 6, which is 29.7. So, that way we can get the value of the median or an estimate for the median. On the other hand, suppose there is one additional element, namely 49.5. Therefore, the ordered sample is now x 12 is 49.5, because that is the maximum of all the elements, but in this case n plus 1 p is equal to 6.5, which is between 6 and 7. Therefore, by the concept of linear interpolation, we get an average of these two, which is the value 30.95. So, this is going to be the estimate for median. Instead, if the new data, the 12th data would have been 16.3, then what would happen? Then we get the ordered sample is like that. So, we can see that 16.3 is coming here, but in this case the median is going to be the arithmetic average of these two, which is going to be 27.9. So, that is going to be the point estimate for the median. Therefore, we can see that a single observation may change the estimate of the central location of the distribution, which is true even for parametric inference, because in that case the sample mean is going to be the estimate for population mean, and therefore, one single value can change the estimate of the central location. Therefore, the most important concept is testing of hypothesis. So, in testing of hypothesis, it differs from the concept of estimation in the following way. Here, based on a random sample of n observations, let me call them x 1, x 2, x n, our aim is to estimate m, the central location of the distribution, by some value m naught. M naught is an estimate which may be based on the sample or which may be theoretically one can think of, and determine the answer to the following question with certain level of confidence. Does this sample provide strong evidence that m is at the point m naught? So, those who are familiar with statistical inference, you understand what I mean, and those who are not very familiar, let me tell you what we try to do here. We want to see that if a given value m naught can be considered as the central location, and if we can, then what is going to be the level of confidence. So, let us go and study. So, more theoretically we shall write it as follows. This H naught is called the null hypothesis. As I have indicated, H naught is the notation for null hypothesis. So, the hypothesis that we want to test is whether m can be considered as the value m naught, and we are going to accept or reject this hypothesis vis-a-vis some alternative which can be of three types. M is less than m naught, that is, the sample evidence is such that we cannot accept that the value of m is m naught, rather it can be that m is less than m naught, or it can be m is greater than m naught. These two are called one sided, or we can think of m is not equal to m naught, which is a two sided alternative. These alternative hypotheses are denoted by H 1. For example, suppose I have n samples x 1, x 2, x n, and we have taken a sample with n is equal to 16, and I am giving you the values of the 16 observations, that is, you can see the 16 values here, and we want to test at 5% level of significance whether we can accept the value m naught is equal to 10 against the alternative is m naught is less than 10. That is, we are looking at one sided alternative. Two important tests in this regard are one sample sign test and one sample Wilcoxon signed rank test. So, in this lecture we shall be studying these two tests in detail. Each test defines its own test statistic based on the sample and has its rule to accept or reject the null hypothesis H naught. Also, we shall see a paired version of both the tests, which perhaps we shall do in the next class, but let us first see what these two tests are. So, the first test we are looking at is one sample sign test. By one sample we mean that the sample is taken from one population. Later we shall see that we will be learning tests which are based on more than one sample. For example, two sample sign test, when we will be comparing the central location of two different populations. So, let us first understand what one sample is, what one sample sign test is. It is one of the simplest of all non-parametric tests. The distribution is assumed to be continuous. So, this is the most basic assumption, that we are not looking at a discrete population, rather it is a continuous population, but the test is actually very simple as we see now. So, what we do here in one sample sign test is the following. It considers the differences between the observed values x I and the hypothesized median m naught. What does it mean? So, suppose these are my observed values and suppose this is my hypothesized value m naught. So, we want to see with respect to m naught how the observed values are distributed. So, in order to test that, what we do the following: the data is converted into a series of plus and minus signs according to the sign of x I minus m naught and stating whether x I is greater than m naught or x I is less than m naught. So, if the observed value is more than m naught, then x I minus m naught is going to be a plus, and if it is less than m naught, then it is going to be a minus, and therefore, we reduce the observed sample into a sequence of plus and minus. Therefore, what happens? We can check what is the number of pluses, that is n plus number of x I such that x I is greater than m naught, and n minus, that is number of x I such that x I is less than m naught. So, here we are checking number of x I which are greater than m naught, here we are checking number of x I which are less than m naught. In case some observations x I is same as m naught, then we ignore that value, because in that case x I minus m naught is going to be 0, and if it is a continuous distribution, we can assume that the random variable taking a particular value has probability 0. So, that is the reason. Now, under the null hypothesis, let us see what happens. M naught is the unique median of f x, let x be the underlying random variable and f is the CDF, that is the cumulative distribution function. Therefore, probability x is greater than m naught under the null hypothesis is same as probability x is less than m naught under the null hypothesis, and that value is equal to half. That is very easily understandable, because if m naught is the true median, then we would expect half of the observation will be here which are greater than m naught, and other half will be here which are less than m naught. All these are going to give me plus signs and all these are going to give me minus signs, right. Therefore, under H naught, the distribution of n plus, which is the number of observations giving plus sign, is a binomial distribution with parameter n and 0.5 is the probability of success, and where n is the number of observations. So, if the sample is truly coming from the distribution with median is equal to m naught, then we would expect that nearly half of the sample observations are going to be greater than m naught and nearly half of the observations are going to be less than m naught. That comes under the null hypothesis, that is the median is actually at the point m naught. So, let me illustrate. Suppose this is the scenario, m naught is the hypothesized median. So, these are the observations which are greater than m naught, these are the observations which are less than m naught, and if m naught is truly the median, then n plus is equal to or very close to n minus. They need not be equal, because we know that statistically it cannot happen that both the sides will have equal number of observations, but there should be a limit. That is what the test is all about, whether the difference that is there in the number of pluses and minuses is acceptable under the null hypothesis. So, in this case it appears that they are more or less same. So, we are likely to accept that m is same as m naught. Now, consider this scenario. Suppose this is my hypothesized m naught, and after we take the differences and convert the observed sample into pluses and minuses, we can see that there are so many plus and so less number of minus. That is, the number of plus sign is much greater than the number of minus sign. Then what we feel? Because it is a continuous distribution, I can see that our observation has come in this range, therefore, we would expect the median is going to be somewhere here, that is actual median of the population is greater than the hypothesized median m naught. I hope you understand this. In a similar way, suppose the situation is somewhat like this, this is the hypothesized m naught, and then we can see that number of n, the number of positive or number of plus signs of n is less than, much less than number of minus signs. Therefore, what we would expect that the median should come somewhere here, because it is a continuous distribution in this range, and therefore, we would feel that m is actually less than m naught. Therefore, we reject the H naught, that is the null hypothesis, in favor of m is less than m naught, that is one sided alternative, if either n plus is too small or alternatively n minus is too big. Say for this example, if n plus is too small, then we would expect that it is more likely that m is less than m naught, or in other words, if n minus is too big, then we would expect that m is somewhat less than m naught, and therefore, we would reject the null hypothesis in favor of m is less than m naught. In a similar way, if n minus is too small or alternatively n plus is too big, then we would rather think that m is greater than m naught. So, something like this, we would expect that m is somewhere greater than m naught. Therefore, if the observed statistic is something like that, that n plus is too big or n minus is too small, then we would expect that m is greater than m naught. For a two sided alternative, m is not equal to m naught. If any one of them, n plus or n minus, is too big or too small, we tend to reject the null hypothesis in favor of the alternative m is not equal to m naught. So, let me illustrate with one example. Consider the sample of size 16 taken from a population. So, there are 16 observations, as you can see enlisted here, and we want to test whether this sample is from a population with median is equal to 10. Therefore, we are testing m naught is equal to 10 against, say, alternative is m naught is less than 10 and our level of significance is 5%. So, what we do? We do the following: we construct the table, we are considering the sign of x I minus m naught, our m naught is equal to 10. Therefore, what we do? 6.10 that gives a minus, 7.80 that gives a minus, 10.10 that gives a plus, and like that we compute it for all the 16 observations. Therefore, what is the value of n plus? N plus is 1, 2, 3, 4, and therefore, quite naturally n minus is going to be 12, because we have 16 observations, and n plus plus n minus is equal to n, the total number of observations. Note that if some of the observations are same as m naught, we have to discard them. So, I write discarding x I equal to m naught. So, all those observations which are equal to m naught, we have to discard them. Therefore, the test statistic we can consider to be n plus. There is no hard and fast, but typically the smaller of these we try to use as our statistic, and we need to check if it is too small. So, if it is too small, that means it is so small that it is very unlikely to happen under the null hypothesis, then we are going to reject the null hypothesis in favor of the alternative. But how to do that? For checking that, we consult a binomial table of 16 and p is equal to 0.5. Now, all of you I assume are familiar with different statistical tables like normal table, chi-square table, T, F, etc. For parametric, these 4 tables are most important, and with that we can test most of the hypotheses that we are going to test. In case of non-parametric, for different tests we need to have corresponding tables which will give us the probability. So, for sign test we have to use the binomial table, and which gives us the probability of our success in n independent trials with probability of success is equal to p. So, that is a general binomial table. For sign test we need to look at p is equal to 0.5. So, consider this table. I am just giving you for n is equal to 16. Similar tables are there for different values of n. On the header we can see different values of p starting from 0.05 to 0.50. For this example, our consideration is 0.50, n is equal to 16. So, we are looking at for different values of x, what is going to be the cumulative probability. Say for example, for the value of 4, the cumulative probability is 0.0384. What does it mean? This means that if x is a binomial 16, 0.5, then probability x less than equal to 4 is equal to 0.0384. Just for the sake of completeness, let us look at what is the value at 15. It is showing that if x is binomial 16, 0.5, then cumulative probability is less than x is less than equal to 15 is equal to 1. Some of you may think how it can happen, because if x is binomial with n is equal to 16, then there is a positive probability that x will take the value 16, but we know that probability x is equal to 16 is equal to half to the power 16, which we consider to be almost close to 0. That is why at this point this is given to be 1. I would suggest that you go to the table and try to see the cumulative probabilities, and if you are try to experiment, you can compute these values for some x, for some n, say n is less than 16, you can take it to be 5 and try to compute the values of probability for any given value of p and for a given value of x. What is going to be the cumulative probability for that one? That will be a good exercise, and that will tell you how one has computed such large tables for different n and different x for different values of p. Okay. So, let us go back to our test. So, for this problem we have to check the cumulative probability of binomial 16, comma 0.5 is taking a value less than equal to 4, as I have already explained, and we observe that the value is equal to 0.384. So, this is what is called the p value of the test. So, that is the observed value of the probability corresponding to the statistic that is given from the sample. Since this value is less than 0.05, we will be rejecting the hypothesis at 5% level of significance. So, if you do not understand this, so let me give you an illustration. So, if it is a binomial distribution with p is equal to 0.05, it is going to be very symmetric around the mean, and we are looking at 5% level of significance. That means, if this is the cutoff above which there should be 95% of the observations, but in this case we have found the value to be 0.03, which is less than for alpha is equal to 0.05, that is 5%. Therefore, because it is a one sided test and this value is less than the cutoff point, we are going to reject the null hypothesis. Later we shall see some examples when we will be looking at the upper sided test, and we shall reject the null hypothesis if the observed value falls somewhere higher than this value. This is called the critical value. I am sure most of you are familiar with this term. So, I am giving you a brief idea about what we do when we are going to test a particular hypothesis. Now, we can do normal approximation, because we know that from central limit theorem that if the number of observation is somewhat large, then we can approximate it with normal. In this case, typically if the value is greater than or equal to 15, then we try to approximate with a binomial distribution with a normal distribution. In order to approximate any distribution with normal, we need to understand what is going to be the mean and standard deviation of the random variable. In case of a binomial NP, we know that the expectation is equal to NP and the variance is equal to NPQ or NP into 1 minus P. Therefore, the standardized variable is S, where S is the statistic. In this case, we have taken n plus. Therefore, we are looking at S minus NP upon root over NP into 1 minus P, and this is going to be approximated by normal 0, 1. Therefore, n plus has a binomial distribution parameters with n and 0.5, then we can consider z is equal to S minus n by 2 upon root over n by 4 to be normal, and therefore, we can use z test. But sometimes we use continuity correction, because it is a discrete density. Therefore, we use a factor 0.5, and under continuity correction this is going to be the statistic S plus 0.5 minus n p upon root over n into p times 1 minus p. So, for the given problem, our S was 4 with a continuity correction 0.5, n p is equal to 8, because n is equal to 16 divided by root over 16 p into 1 minus p, and that gives us the value. This should be 25, and therefore, the obtained value of the statistic is equal to minus 1.75. So, since the cumulative probability is of minus 1.75 is 0.04, we reject the null hypothesis at 5% level of significance. What does it mean? Those who are not familiar with this, for them let me explain. We go to the normal table and the observed value of the statistic, if you look at it, it was minus 1.75. So, we go to the normal table, we look at minus 1.7 and 0.05, we come to that value which is equal to 0.04006, which is approximately 0.04, which is less than 0.05. Therefore, we are going to reject the null hypothesis under normal approximation as well. So, as I said, it was a very simple test which is called sign test, and like that we can check whether we can accept the null hypothesis that m is equal to m naught. Now, let us look at a slightly improved test which is called Wilcoxon signed rank test. Sign test is very simple, but it has one problem. As I illustrate here, suppose with respect to some data we are testing if m naught is equal to 10, that is the hypothesized median is equal to 10, and we have taken 5 observations. Suppose these observations are 7, 8, 10, 12 and 14. In this case, what is going to happen? We will have minus minus, this is 0, we can ignore, plus plus. So, number of plus sign and number of minus sign are same, and we can feel that therefore, we can accept 10 to be the median of the population. Suppose on the other hand, my observations are 7, 8, 10, 18 and 20. If we use simple sign test, then again we will get minus minus, this is 0, plus plus. Therefore, by sign test it also has the same value as this, hence we are going to accept the null hypothesis that m is equal to 10. However, if we look at this, that it is a continuous distribution and observed values are from 7 to 20, then we can easily feel that the median should not be 10, it should be something higher than that. That is a basic intuition. Hence, what I am saying that under the continuity assumption, A does not seem to reject H naught, because both of them are giving 2 minus and 2 plus. Therefore, A does not seem to reject H naught. This sample is not going to reject the H naught, but it feels intuitive that the B population median would be greater than 10, as I have already explained, but sign test would give the same output for both, as I have already explained. Therefore, we need to do something better, and we introduce the concept of rank order statistic. What is that? The rank order statistics for a random sample are any set of constants which indicate the order of the observations. So, we are not just looking at it is plus or minus, we are also looking at the value. That means, in this case whether it is not greater than or less than m naught, we are looking at how much it is greater than m naught or how much it is less than m naught. So, that is what we will be computing, which is called a rank order statistic, and from this rank order statistic the basic test that comes up is called Wilcoxon signed rank test. So, let us first study one sample Wilcoxon signed rank test. What it is? So, as before, we have a random sample of k observations from a continuous distribution with median is equal to m. So, this is the population median, we do not know about it. This is what we are trying to estimate or we are trying to test based on a sample. But to apply Wilcoxon signed rank test, we need another additional assumption that the distribution is symmetric around the median. It is not necessary that all distributions are symmetric about the median. For example, if it is a positively skewed distribution, then median may come somewhere here and we can see that it is not symmetric around that median, but that will not work for applying Wilcoxon signed rank test. So, this assumption is needed and we are testing H naught m is equal to m naught against an alternative which can be one sided or two sided. This I have already explained, so I am not going to repeat that here. What we do? We consider the difference d I is equal to x I minus m naught. Each d I may be positive or negative. Again we ignore zeros in d I, since the probability of 0 to occur in a continuous distribution is nil in theory. Because it is a continuous distribution, the probability that x is taking the value m naught is 0, therefore, we ignore the 0 values when we are considering d I. Now, what we do? We look at the absolute value of the difference d I for all the n observations x 1, x 2, x n. Let t plus be the sum of ranks of the positive differences and t minus be the sum of ranks of the negative differences when we arrange all these di's in ascending order of magnitude. What will happen if ties are there, t plus and t minus? Say for example, my m naught is equal to 10 and suppose x 5 is equal to 12 and suppose x 9 is equal to 8. Therefore, d 5 is equal to 2 and d 9 is equal to minus 2. Therefore, modulus of d 5 is equal to modulus of d 9 is equal to 2. Therefore, in the ascending order of the di's, these two will be tallying. What to do? What we typically do is, we assign the average values there, as I will explain later. So, sometimes in case of tie of ranks, each tied absolute value is assigned the mean of the ranks that would have been allotted in case of no tie. So, if there were no tie, perhaps one of them would have got the rank I, other one would have got the rank I plus 1, then I will give the average of these two to both of them. So, that is the idea. Therefore, t plus plus t minus, assuming there is no tie, or if there is a tie we break it like that, is equal to sigma I is equal to 1 to n of I, that is n into n plus 1 by 2. Now, let us see what happens under H naught. Under H naught, t plus and t minus should be close, because if this is the m naught and these are my observations, what I would expect, the ranks of the differences is going to be equally distributed. Therefore, the sum of ranks of the negative ones and the sum of ranks of the positive ones should be very close. So, in contrast to the ordinary one sample sign test, the value of t plus is influenced not only by the number of positive difference, but also by their relative magnitudes. So, I hope you understand that, otherwise I will explain later. Let t be the smaller of t plus and t minus. If true population median exceeds m naught, the sample data would reflect this by having most of the larger ranks corresponding to the positive difference. So, let me explain with a very similar diagram. If m naught is the true median, then in this scenario perhaps this is going to get the rank 1, this is going to get the rank 2 If both of them are going to get 3 and 3, then I would rather give 3.5 and 3.5. Like that, we would rank all of them. Therefore, as we can understand from this diagram, T plus, which is the sum of ranks of the positive ones, is going to be approximately close to the sum of ranks of the negative ones under m is equal to m naught. But suppose the situation is somewhat like this, we would expect the alternative is like this, but the observation is such that there are so many positive signs here and so few negative signs here. Then what will happen? All the higher rank values are going to be to the positive side. Therefore, T plus is going to be much higher than T minus, and then we would expect the actual median is greater than m naught. In a similar way, if we get a situation like this, then all higher rank values are coming with negative signs. Therefore, T plus is going to be much less than T minus, and we would expect that actual median is less than m naught. So, we will have very similar type of testing procedure. Let T alpha be the critical point corresponding to alpha, and we are testing H naught m is equal to m naught. So, if the alternative is H 1 is m is greater than m naught, then we will reject the null hypothesis. If T minus is too small, that is T minus is less than the critical value T alpha, where alpha can be say 5% or 10% or 1% depending upon how you are going to test. Similarly, we will reject null hypothesis in favor of m is less than m naught if T plus is too small, and for a two-sided test we will look at T plus is less than or equal to T alpha by 2 or T minus is less than T alpha by 2. That is, if any one of T plus or T minus is very small, then we are going to reject the null hypothesis. The p values are calculated using the general definition. So, some of you may not know what is the p value. The p value is the observed value of the T plus under the null hypothesis. So, let me give you an example. Suppose we have 20 observations which are like this. We want to test if it is coming from a population with median is equal to 9.9, and we are looking for a two-sided test that H 1 is m is not equal to 9.9, and suppose the significance level is 5%, that is alpha is equal to 0.05. How do you solve it? So, let me go to the solution. What we do? We prepare a table like this. So, first value is 9.3, m naught is 9.9. So, di is equal to minus 0.6. Therefore, what we understand that it is negative, but not only that, the value of the absolute difference is 0.6. Similarly, for 8.8, it is minus 1, and the value of di is equal to 1.1. On the other hand, if it is 11.5, then the difference is 1.6, it is a plus, and the absolute value of the di, and like that we calculate it for all the 20 values, and we get the plus and minus sign, also we get the absolute value of the di, and then we rank them, and we have taken up the ties by assigning equal weight to them. Say for example, 9.8 and 10, one is giving me di is equal to minus 0.1, other is giving me the value to be plus 0.1, and that is the smallest. So, one should get the value 1, other should get the value 2. We are equally distributing them between these two. So, both of them get the rank 1.5. Similarly, you see that if one observed value is 9.9, which is equal to the m naught, in that case we are ignoring this and we are giving a value 0. So, that observation will have to go out of my consideration. Therefore, we will be working with only 19 observations. Now, what we do? the updated value of n is equal to 19. Now, we calculate the sum of ranks for positive ones, which is 99.5, the sum of ranks of the negative ones, which is 90.5. So, typically we take minimum of these. So, in this case the test statistic t is equal to 90.5. Now, the question comes whether we should accept the null hypothesis or reject. Therefore, we go to the table, in this case Wilcoxon sign rank table, which is available in this location. This is available over the internet, you can refer to that, but for your understanding I am showing some portion of the table. N is equal to 19 at 5% level of significance. It is a two-tailed test because we are testing m is not equal to m naught. Therefore, the critical value is coming out to be 46. Therefore, we shall reject the null hypothesis if that statistic t comes out to be less than 46. But what we have got? We have got the value 90.5, which is greater than that. Therefore, we cannot reject the null hypothesis. So, that is the conclusion after this test, that we cannot reject this null hypothesis if that is the sample that we have got. Let me now give you a very interesting example involving sign test and signed rank test. Consider the following sample of size n from a population. So, the data points are 2, 2.5, 7.5 like that up to 14.5, and we want to test whether the population median is 4.5. That means, we are trying to check if this data is good enough to support the claim that the data has come from a population whose median is 4.5. That is somewhere here. What is going to be the alternative? Looking at the data, it appears that it should not be at 4.5, rather it should be somewhere bigger than m naught, that is 4.5, maybe somewhere like this. Therefore, quite naturally the alternative is going to be m greater than m naught. So, we shall apply both sign test and Wilcoxon signed rank test for testing the above hypothesis. So, let us first consider sign test. We know that we reject H naught with a level of significance alpha if m is less than m naught is my alternative hypothesis. Then we shall look at n minus, and that should not be too big, but if m is greater than m naught is the hypothesis, then we shall look at if n plus is too big or n minus is too small. So, let us compute the following. In sign test, we are just taking the difference from the observed value of the median and looking at the sign. Therefore, for 2.0 and 2.5 we have got negative sign, and for all remaining ones we have got positive sign. Because number of observation is 9, therefore, n plus is equal to 7 and n minus is equal to 2. Therefore, what we have to do? We have to look at binomial table with parameters 9 and 0.5 and to see whether we can accept the null hypothesis or reject. So, this is the binomial table, and we have got n minus is equal to 2. So, we are looking at the cumulative probability that a binomial 9, 0.5 variable takes value less than equal to 2. From the table we get when n is equal to 9, the cumulative probability for 2 is 0.0898. Since this sample p value, which is 0.0898, is greater than 0.05, therefore, we accept H naught at 5% level of significance. So, this I have explained to you. Let me just illustrate it once more. So, suppose it is the binomial distribution with 0.5, it is going to be symmetric. So, p value is 0.08, but the critical value for 5% level is somewhere here. So, if the value is lesser than this, then only we will reject the null hypothesis, but that did not happen in our case. Therefore, we accept the H naught, or we cannot reject the H naught against the alternative H 1. Alternatively, if we had taken the test statistic to be n plus, then we will have to look at the probability that a binomial 9, 0.5 variable is taking value greater than equal to 7. So, let us look at the binomial table again. Till 7, we need to find out the probability that a binomial 9, 0.5 taking a value greater than equal to 7, which is nothing but 1 minus probability that the random variable is less than equal to 6. Therefore, we look at the cumulative probability that a binomial 9, 0.5 variable is taking the value less than equal to 6. So, that value, if we look at the table carefully, is given as 0.9102. Therefore, probability is 1 minus probability binomial 9, 0.5 is less than equal to 6 is equal to 1 minus 0.9102, which is coming out to be 0.0898. Therefore, again by the same logic, we cannot reject the null hypothesis. That means that if we are going to use sign test, we are not able to reject the null hypothesis. That is what we have written. The outcome of the testing is that the null hypothesis cannot be rejected at 5% level of significance using sign test. Now, let us look at what happens when we use Wilcoxon signed rank test. We already know this thing. This you have already seen, that the critical region for alternative m is greater than m naught is going to be that reject H naught if t minus is too small. So, t minus is the sum of ranks of the negative ranks. Therefore, t minus is the sum of ranks of all those differences which are negative, that means which are less than the median m naught. Therefore, we compute the statistic as follows. We have the values given like this, then we are subtracting 4.5 from all of them. Therefore, we got these two are negative, all these are positive, but not only that, we have to look at their ranking in absolute value terms. So, 2 is the smallest, therefore, this is the getting the value 1, 2.5 is the second smallest, it is getting the value 2, 3 third smallest, it is getting the value 3, and like that till this point we have got 9. Therefore, t plus is equal to sum of ranks of all those ones which are positive, and that is therefore is going to be 3 plus 4 plus 5 up to 9, which is coming out to be 42. On the other end, t minus is equal to 3, because it is the sum of 2 and 1. Therefore, we look at now this one tilt test with 9, and here the critical value is given out to be 8 for alpha is equal to 0.05. Our observed value was t minus is equal to 3. Therefore, at 5% level the critical value is 8, but t minus is less than that, and therefore, what we do? We have to reject the H naught at 5% level of significance using Wilcoxon signed rank test. That is why I said that this is a very interesting example, because when we are using sign test, we are going to accept the null hypothesis at 5% level of significance, but when we are using signed rank test, we are able to reject that one. And if we had looked at the data, we found that it is natural intuition is that 4.5 cannot be the median of that test. Therefore, in that sense signed rank is more powerful than signed test. Normal approximations, like the case of sign test, here also we can do normal approximation if the sample size is somewhat large. So, the formula for normal approximation is as follows. So, let us assume that n observations are there, assume that there are no ties. Therefore, all the n di's will have different ranks, and they are going to be 1, 2, 3 up to n. Now, each of those observations is equally likely to go to either the positive side or the negative side, because it is the median that we are testing. So, probability half, it will be greater than median, with probability half it is going to be less than median. So, let us consider a Wi corresponding to each observation. So, if xi is the observation and Wi is something which is a Bernoulli random variable, which is giving us the value if it is going to the positive side or it is going to the negative side. So, Wi is equal to 1 if di greater than 0, Wi is equal to 0 if di is less than 0, a typical Bernoulli distribution. So, under H naught, that median is equal to actually m naught, xi minus m naught is going symmetrically distributed about 0, since x is symmetrically distributed about m is equal to m naught. Therefore, probability Wi is equal to 1 is equal to probability Wi is equal to 0 is equal to half. Therefore, expected value of Wi is equal to half and variance of Wi is equal to 1 by 4, that we know from the definition of Bernoulli random variables. Therefore, t plus is equal to summation of Wi into rank of di. What it is going to do? It is going to consider only those which are positive and adding up their ranks. If it is less than the median, the value of Wi is 0. So, therefore, it is not coming to the summation. Therefore, expected value of t plus is equal to summation over I is equal to 1 to n, expected value of Wi times the rank of di. Therefore, it is 1 times half plus 2 times half plus n times half, because of the linearity of the expectation, which is equal to n into n plus 1 by 4. In a similar way, therefore, the variance of t plus is going to be variance of Wi into rank of di square, because the observations are independent. Therefore, we are not considering any covariance terms. Therefore, it is 1 square times variance 2 square times the variance plus n square times the variance 1 by 4. So, this is coming out to be n into n plus 1 into 2n plus 1 upon 24. Therefore, for a larger values of n, say n is greater than 25, values of which are not available in the Wilcoxon sign rank statistic table, we have to approximate it with the following statistic: t plus minus n into n plus 1 by 4, which is the mean, divided by n into n plus 1 into 2 n plus 1 upon 24, which is the variance. Therefore, its square root is giving us the standard deviation. Therefore, this whole thing is distributed as normal 0, 1. Therefore, for larger values of n, we can convert the statistic to a normal 0, 1 distribution, and from there by reference to the normal table we can accept or reject the null hypothesis. Okay friends, I stop here today. I hope I could make the concept clear about how to apply sign test and sign rank test for testing the central location of a unknown distribution. As I said at the beginning that similar tests can be used for paired data, but for that you have to understand what a paired sample is and what is the significance of a median there, and how we can apply the sign test and sign rank test for a hypothesis with respect to paired sample. Okay students, in the next class I shall start with that. Thank you.